Hello and welcome to a short overview of the paper Universal Physics Transformers, a framework for efficiently scaling neural operators. My name is Benedikt Alken and this is of course joint work with some colleagues from the Johannes Kepler University in Linz. So, short overview of the what are we doing in this paper. We are tackling neural operators to learn physical simulations, and in the current landscape of neural operators, mainly the focus is on relatively small scale problems, so with like 1K to 10K inputs. However, the interesting problems really start to get going at like tens of thousands, hundreds of thousands, or even millions of inputs. And we introduce a framework to efficiently scale these neural operators up to tackle these large-scale simulations and large-scale input sizes, where we use reduced latent space modeling as a key motivation for this scaling up. And we also introduce new methods to make it applicable to Eulerian, so grid-based simulations, and also Lagrangian, so particle-based data. Um, all with throughout the whole method and the whole paper, we leverage the scalability of transformers to really make use of these scaling properties. So, short background, what are neural operators in classical machine learning, classical under quotes? Um, we want to approximate some function and or we assume that we have some function of the underlying world. So we have some measurements indicated here by the points, and there's probably some noise in there, so we not can't fit the or we can't measure the function perfectly, but with some noise. So we try to then approximate with a machine learning model the ground truth underlying function, but since there's some noise, we will get some errors. And then during inference, we want to evaluate this function at various points, so on unseen data. So we can just evaluate this function wherever we want, even if this data point has not been in our training set. So we basically the mapping is we map a scalar x or like some data x to some finite data y. However, in neural operators, we want to map infinitely many data. So we want to map functions, one function to the next one, to another function. And how we do this is we have some function. So let's say we have some simulation state, some particle state or whatever, and we discretize it into particles. But there is an underlying function that we don't know of. So for simulating the systems, we have to discretize it into either mesh points for like Eulerian data or grid-based data. And for particles, we have the particles anyway, which is a form of discretization of the underlying functions. And in order to process that, we need to use this discretization to approximate the source function, and then a neural operator transforms this function into the next or into another function. And what we then do with this function is we also evaluate it at arbitrary positions. Notably, the input positions and the output positions don't need to match, so they can be, since we are dealing with functions here, we can evaluate it at any point. And then when we train these models, we simply have some ground truth function and or we will make some approximation errors as you see on the light green bar here. So we won't match the ground truth target function perfectly, but we have some measurements on that. And with these orange arrows, we draw or we pull the two functions together, the ground truth function and the predicted function. And then we can basically evaluate it also in the same time. However, there's one important thing that classical physics simulations have a very big constraint on. So, as we indicated here, for a neural operator, we can deal with arbitrary many inputs and outputs. We don't necessarily need a very fine discretization. This is not the case for classical physical simulations, where the underlying equations require that the spatial resolution and also the time resolution, as we see afterwards, requires to be quite finely resolved in order to preserve the numerical stability and in order to not have the physics manipulated behind it. Because, for example, if two particles collide and the particles are resolved at a very coarse time scale, they would at some point collapse and be submerged within each other, and then basically it's a very large amount of force would push them away, and that's not really physical, or that can't really happen in the physical world. If you think of like glass particles or something, these are very hard, so they can't really submerge into each other without actually breaking. So we need very fine resolution, spatial resolution. So we need a lot of mesh cells for Eulerian data, or like particles in the particle simulation case. But in machine learning, we can oftentimes leverage a very coarse grained resolution. And what I mean with fine-grained resolution in most cases is not only the spatial resolution, but also the time resolution. So when we transform one function to the other function with a classical solver, so when we transform the discretizations of these two functions towards each other, we actually don't make these large steps, but we make very small steps towards it. And this is to preserve the numerical stability and the physics out of it. And this visualization is not really accurate because the actual timescale that numerical solvers or classical physics solvers operate on is really, really tiny. So it would more look more like this, or such that you can't even see it. So it would be like very small time steps. These are typically in the hundreds of thousands of time steps that a classical solver would need in order to make one machine learning step, so to say. So machine learning can operate on much coarser timescales because they simply approximate it, and not with the classical physics, but with some learned function from data. So to visualize this, we can have here the small time steps in blue, which the classical time solver takes, and the large time steps that the neural surrogate or a machine learning model would use to solve these simulations in orange here. This provides a very large speed up, and neural surrogates can often operate on orders of magnitude faster speeds than classical solvers. Another thing as a background is that of reduced order modeling. So when we look at these simulations, we typically require, since we require this fine-grained resolution for the classical solver, the underlying equations or the underlying system is more or less can be described in a much lower dimensional way. So when we look at this simulation here, for example, we see 400 2D vectors, so 800 scalars that describe this system, but we could also represent the system as a more abstract way, in a more abstract way, as for example the description force walls. So we wouldn't be able to perfectly reconstruct this, but we get a very good estimate of the underlying system state. With even more dimensions, so force worlds that are operated in counterclockwise measure or clockwise measure, we could describe this system more in detail. And as we add more dimensions, we will approach or we don't need 800 words to describe the system, but we can typically leverage with much fewer words. So with that background introduced, let's get started with actually what we are doing in our paper. So in the current landscape, the neural operators that are out there are typically don't very scalable to large system sizes. So when we look at the memory consumption for a single training step, we're training with just a single item, things like graph neural networks or even transformer on the original input space quickly explode in terms of memory and would require an extreme amount of compute to even train systems that are in the hundreds of thousands of particles or mesh cells. In contrast to that, some methods also introduced some latent space, some reduced latent space modeling. Here in the example, this is GINO, geometry informed neural operator, which projects everything down onto a regular grid and then operates on this regular grid. However, in the 3D case, these 3D regular grids are also not very scalable, so they also quickly require a lot of memory and are not that scalable. In contrast, UPT makes use of much more flexible latent space encoding and can therefore operate on much higher particle counts and scales much better to larger systems. How do we do this? So we have some input data that is on an irregular grid, some 2D data, some 3D data, whatever you want. And then we discretize it into some, well, not we have some discretized data out of this, which comes from the numerical solver. And then we encode this discretized data into some function with the encoder. We do this with basically getting the features of the simulation, so 3D positions or even pressure or velocity in the fluid dynamics case. And we add some the ground truth position to it, so we encode this with transform positional encodings. Then we get to some latent representation of our input system, and then a module called the approximator approximates the solution at the next time step. So we propagate this latent space forward, these latent tokens forward in time until some time step in the future has been reached, and then we can decode this solution again with a cross-attention decoding, which then takes some positions. So we decide what positions we want to evaluate on, and then evaluate the latent space pointwise in the neural field-like approach. And to visualize this a bit better, so first we have our encoder. Our encoder has some discretized data from the underlying function. It approximates this underlying function. Then the approximator maps this underlying function to the next time step, so to another function. And then the decoder takes this function from the approximator and evaluates it at certain time steps, or sorry, not at certain time steps, but at certain positions of the function to get then the discretized data. And we compare this then to the ground truth. So here in green and light green is the decoder output, and the darker green would be the ground truth values. So we align these two things for the discretization of these two functions. We align these two with a normal mean squared error, and with this we can train our neural operator. And one question that I have left out is, how do we actually encode 3D point clouds? So we take our input system, which might consist of some particles or some mesh cells. We then do some data augmentation in the form of subsampling, which can be thought of like masking, which is also very prominent in the vision community. We then select some supernodes. So we elect some supernodes where we say that these supernodes should correspond or should be representative of their local region. We then pool everything around this in a radius. So we create a radius graph around this, and we pool all the input points from this radius to the supernode via some message passing. So this is just a simple one-layer message passing layer that aggregates this local information onto these supernodes. We then have a set of supernodes, which is much fewer in size than the original inputs, which we can aggregate then global information. We do this via a simple transformer or some transformer layers. And then after we aggregate some global information, we further reduce it for computational reasons and for computation efficiency reasons into an even lower dimensional latent space with a perceiver pooling layer. Now, how does this all come together? So as explained, we have this encoder that has first a supernode pooling layer, then some transformer blocks and a perceiver pooling to compress everything down into a really low dimensional latent space. We then have the approximator that propagates this latent space forward in time, and the decoder that decodes this latent space at some arbitrary position, at some arbitrary spatial position. What we additionally do for training, so we don't really enforce this training procedure here wouldn't really enforce like some separability between encoder and decoder, because what's the difference between the transformer blocks of the encoder and the transformer blocks in the approximator? So we need to enforce some kind of responsibility to each component to really make sure that we can do this propagation in time. And what we came up here is we call this type of latent rollout. So we do all the rollout, the time rollout in the latent space. So we encode our data into some latent representation CT. However, we immediately decode it again to enforce that the encoder really only is tasked by encoding the discretized data into some function representation, where C would be the representation of the underlying function. With decoding again, we ensure that the decoder and the encoder together force an identity function. We also plug the CT into the approximator to predict the next time step or some future time step. So the function at the future time step, which is again decoded for the normal next step prediction basically, but we also immediately encode it again in order to again match the latent codes for this. So with these two identity functions of the encoder and decoder, we enforce the separation between encoder, which should only encode the discretized data into some function representation, the decoder, which is the inverse, which takes the function representation and should decode it or in some discretized physics representation, and the approximator should only propagate it forward in time. With this, we can do a lot of cool things, namely that we can speed up the simulation even more because we don't need to decode the latent space at each time step. So we can do, for example, every fifth time step only to visualize it still in a quite high resolution, and this greatly speeds up things. What it additionally does is it allows us to train models on Lagrangian data. So with particle simulations, when we approximate the underlying function and not track each individual particle movement as we do in UPT, so we approximate not the individual particle movements, but we more approximate the underlying function, how particles move, then we would need some kind of positional information during inference where the actual particles are. However, this is not really possible. So when we would do it in normal training, because we don't really have ground truth particle positions. And in this way, we can easily just roll out over the latent space and query the latent space at an arbitrary position to then get a field representation of the simulation. And these things are then can be evaluated at any position, even if it's not in the training dataset, or we don't need the actual ground truth particle positions, but we can just evaluate the latent space at any point in time and space. Now, how do we train these things? So we train these things on a self-generated dataset, which is quite large. So the problem with current datasets out there is that they are typically tailored towards the current state-of-the-art in neural operator learning, which is typically focused on quite small simulations. But in order to showcase our scalability of UPT, we generate a simulation dataset from computational fluid dynamics, which contains 10,000 simulations. It has some adaptive meshing under the hood and contains mesh points between 29,000 and 59,000 points. The simulations always have some inflow velocity from the left-hand side here, with 1 to 4 circles placed randomly in the volume with 2D positions, and this creates then these turbulences on the right-hand side or in the right region of the simulation. Overall, this simulation is rolled out for 100 seconds of simulation time, which corresponds to 100 time steps in machine learning time steps, so to say. However, the number of time steps that the actual physical solver would need are much, much higher. So the time scale of the machine learning model would be 1 second. So it predicts 1 second into the future, whereas the classical solver here, pisoform solver, requires 0.0005 seconds time steps in order to preserve the numerical stability and not collapse. And how does this look compared to different competitor methods? So we compare two baseline methods, FNO and UNIT. In addition, the geometry-informed neural operator, which has this compression onto a regular grid. And in comparison to them, we evaluate on two test metrics, the test MSE, which describes the error of the next step prediction for the test set. Here we outperform all the competitors by quite a large margin, where even the smallest model of UPT is better than the largest model of GENO. And we also evaluate on correlation time, which measures how long can we roll out the simulation for while still being having a high correlation with the ground truth simulation. And also here UPT performs very well and outperforms competitors by quite some margin. To the experienced eye, this might look like GENO has a very strong performance gain from the 17 million parameter model to the 68 million parameter model. However, this is only because UPT is just operates on a much different loss scale, so it's much harder to further improve upon this loss scale, where it's much easier to improve upon something like 3 to the power of minus 2, which we see here in the middle plot, where we train even smaller UPT models, so a 1 million parameter or 2 million parameter model, and we see that at this loss scale that is comparable to the GENO models, we have a similar scaling. So UPT scales also very well with parameter size. What is also interesting is that here on the right-hand side, we train UPT with varying the number of input simulations. So typically we train on the full training dataset, which contains 8,000 simulations. However, here we train also UPT on 4,000 and 2,000 simulations, where we see that even with 2,000 simulations, we are relatively on par with the GENO model that was trained on 8,000 simulations. Now, how does this all look like? Here is a short visualization of what a rollout here would look like at certain time steps. When we compare the first and second row, we see that there is high similarity between all these simulations up until very high time steps. So time step 40, time step 50 looks similar to this. In terms of speed, our method also has a very strong improvement. One key motivation here is, as previously introduced, we are able to roll out everything by the latent space. However, in these grid-based models, we don't necessarily need to. So we also can roll out these things auto-regressively. And compared to traditional solvers, we of course gain a large speed up as it's common in neural operators, where also Geno has a quite large speed up. However, when it really comes to pushing the speed of these models, when we do a latent rollout, we get up to a 400 times speed up over traditional solvers. Very interesting thing about our method is also that we offer a very flexible trade-off between inference time and pre-training time, or inference performance and pre-training time. So we see here in orange how how the training or the test loss behaves when we scale the number of supernodes and the number of latent tokens uh, during training. This, of course, reduces the throughput during inference and also increases the training time. However, we see that we have very nice scaling. The more compute we give it, the better the model becomes. This is also shown when we do compound scaling, so when we scale everything at once, so we scale the number of supernodes and also the number of latent tokens, we get very nice scaling behavior. We also apply this to Lagrangian fluid dynamics, where we show here some two examples for a Taylor-Green vortex, one in 2D and one in 3D. And notably, our model has some kind of paradigm shift where previous models are typically graph neural network based, and they really track each individual particle, and they make iterative updates to the particle positions and therefore track them throughout the whole simulation. Whereas we in UPT, we simply model the underlying physics and we underlying velocity field, which allows much larger timescales that we can propagate forward because we don't need to track these individual particle movements, but we are more interested in the macroscopic fluid velocity or particle velocity field. And this allows us to also compare against these things on things like the velocity error of each particle, where we see that UPT performs very well against very strong baselines in the form of graph neural simulator and SEGNN, which is an improvement thereon. One very cool thing about this is that we really learn the underlying field of these particle simulations, so the underlying velocity field, which we showcase on the Taylor-Green vortex 2D example as shown in top right. So when we zoom into one of these vortices, we can see that our model really learns the underlying velocity field, which we see here by the particles are given by the dark blue dots here, where the velocity is indicated via the arrow, and we can query the UPT latent space at any point in the space. So for example, here we plot simply, or we evaluate simply the latent space on a regular grid, where we plot these white arrows here, and we see that the underlying velocity field that was implicitly learned by UPT matches the actual ground truth movement of the particles quite well. And yeah, with that being said, that's it for the short introduction video. Thanks for your attention and feel free to check out further resources. The paper, project page plus the code is published, and we also have some tutorial notebooks to get you started with UPT. Thanks for listening.